Alright guys, so we got our study guide for test number 2. Begin with some basic unit stuff. Velocity, meters per second. Acceleration, meters per second squared. Speed, meters per second. Displacement, meters. Time, seconds. Gravity, meters per second squared. Just if you're labeling things, this is what you would do. Move into our definitions here. First one being physics, so it's the study of matter and energy. Study of matter and energy. This is nothing new. We've had this quite a few times. Vectors, magnitude and direction. So a vector can be defined as magnitude and direction. Scalar, S got cut out there with the hole punch. Scalars, that's just magnitude. Displacement, it's magnitude plus direction. I would probably say distance plus direction. Probably a better way to say it. Velocity, rate of change of. So anytime we see something per second, we can say rate of change of. And then remember the units for velocity being meters, so it's the rate of change of position. Constant. So constant velocity is the same speed in the same direction. Cruise control on a straight road. Average velocity, total distance over total time. 100 miles an hour, so you travel 100 miles in 1 hour. Instantaneous velocity, it's looking at your speedometer for a fraction of a second. Speed at any one moment in time. More importantly that you take away is that if you have a position time graph and I find a tangent line, that would be my instantaneous speed. So the slope of a tangent line always gives us our velocity. So if we know slope, we know velocity on a position time graph. Acceleration. Once again, it's per second squared, meters per second squared. So really, it's like saying meters per second. Therefore, it's the rate of change of this, which is velocity. So rate of change of velocity. Last time it was rate of change of position. This time it's rate of change of velocity. Free fall, 3 conditions. Starts at rest, 0 meters per second. Gravity's constant, 9.8 meters per second squared, and we don't have any air or vacuum, no air friction. For air resistance, we're back to air friction again. So we have no air friction in a vacuum. And that's the next thing, which is no air, vacuum, no air. You know, space is close to a true vacuum, but not even space is a true vacuum. Terminal velocity, as fast as an object can fall. Different objects have different terminal velocities. If you're a light object with a lot of surface area, you're going to have a pretty low terminal velocity. Derivative, new graph based on slope, and integral is a new graph based on area. So there we go. Let's get into the conceptual now. So for the conceptual, the first question here says, describe the difference between vectors and scalar quantities. Give 3 examples of each. Which quantity is preferred in physics and why? So we come down here and we take a look at our answer. So, you know, vectors are preferred. And the reason they're preferred is because they contain direction. While scalar quantities only have magnitude. The vector is preferred so you can take quantities in 2 dimensions and add them, also known as trig. You know, later this year we'll talk about how we can have a force here, you know, and you can have another force in this direction and a force in this direction. And using the fact that we have vectors, we can add these together. And it doesn't matter the order you add them together, you'll still get the same net force out of this. Well, anyway, that's something we'll do later this year. Don't worry about it for now. Number 2. So number 2 is asking, answer the following questions about free fall. How far does an object fall in 1 second? How fast is it going after a second? Make a position time graph for a falling object and a velocity time graph for the same falling object. These should be things that you just memorize. Of course, you can always solve for these things by using magic physics formulas. So don't forget that. You always have that option to solve using magic physics formulas. One of the things that might come up is, you know, is a magic physics formula the same as a free fall equation? And it depends on how you look at it. If we take a look at number 3, which looks like this, and we put an object that's at rest into the equation, and we make AG, suddenly we have the free fall equation, d equals 1/2 gt squared. That we used in our jumping lab and some different things like that. If I put 1 second in here and plug everything else in like gravity, I get half of 9.8 or 4.9 meters. Likewise, we could take magic physics formula number 1 and we could put in 0 for V naught, and all of a sudden you make AG and you have V equals GT, the other free fall equation. You put 1 in here and you get 9.8 meters per second for the velocity. So, you know, magic physics formulas, free fall equations, you know, they're really the same thing. It's like a special case for a magic physics formula. As far as the graph goes, as long as you make your swirl at the beginning pointing down, or our coordinate system and directional, we end up with a distance of, or we end up with a graph that looks like this, a parabola, more and more and more and more, and the velocity, the rate of change of velocity is constant, 9.8 meters per second squared. Here's the motion diagram. Take a look at number 3. Number 3 says, explain why in a vacuum a feather and a cannonball fall at the same rate. In the real world, do objects continue to accelerate? Why or why not? So we look at the answer to this one. So in a vacuum, you lack air. So all objects accelerate at the same rate, a constant rate of 9.8 meters per second squared. In the real world, you have air, so objects reach terminal velocities. And different objects reach terminal velocity the fastest can fall at different rates. But a lot of times what will happen to this graph is you'll get to a point where you can't fall any faster and it will turn into a straight line. Likewise over here, you get to a point where it can't fall any faster and then you reach a constant V. So that's how that graph would change if you reach terminal velocity. You know, the dots would be the same distance. A lot of your rockets had this happen, and you should be able to relate that to kind of what we saw on our project. Number 4, if we take a look at number 4, number 4 says an object is thrown up in the air at 5. The Earth pulls down on it at negative 9.8. How fast is it going at the apex of flight? What is the acceleration at the apex? So we begin by making a motion diagram. We threw it up at 5, and that means it's going to land with negative 5. That's because the thing that makes it speed up and slow down is gravity, and it's constant. It's not changing. Gravity is negative 9.8. So V apex, always this, 0 meters per second. Acceleration at the apex, don't fall into this trap. Even though it's not moving, the reason that it stopped moving is because of gravity, negative 9.8 meters per second. And then when it lands, the velocity at 0, you'd get negative 5. These are things you don't need to plug into formulas. You should just know, because gravity is constant, you can assume it will land with negative 5. Here's our graphs. Get the parabola, get a straight line, we get a flat line. You know, the slope of this line being negative 9.8. Take a look at the last one, last conceptual here. So number 5 says, an object with constant acceleration is passed by an object with constant velocity. If the object with constant acceleration starts from rest, how many times will they cross paths? Make a graph of position time and velocity time when the two objects cross paths. Can they have the same velocity? Why or why not? So these are our graphs that we get. And this doesn't change as long as they leave at the exact same time. So when they cross paths, as long as they leave, you know, you can't wait even for a fraction of a second, because then you can't assume these things to be true. But the graphs would then change. But the first part is they cross paths twice. You know, they cross here and here. So they cross paths 2 times at 0, and then when they catch each other, we'll call it t. And so when he finally does catch up to him, what happens is he just blows right by him, and that's because he's going twice the speed. So because he gets such a head start, see how far in front of the constant velocity is from the constant acceleration? When they finally do catch each other, I mean, he just blows right by him because he's going twice the velocity. So it's only a fraction of a second they have the same position when they catch each other. So that's pretty much how it goes. In fact, they do have the same velocity at half the time, t half. And you can see that they're at a quarter d and half d here in our graph. So they're not even close to having the same position yet. So that's pretty much it for the conceptual part, and we'll have another video here for the math part.